Today in static fluids, we're going to talk about buoyant forces. What I want you to get out of today's lesson is why do you feel lighter in a swimming pool than when you're on ground? And why do some objects float while others sink? Oh, it's warming up. It used to be 76 degrees in here. So the reason why you feel lighter in a pool is due to this idea called buoyancy. What buoyancy is an upward force due to a liquid. Now, if you remember our last video lecture, we talked about the fact that as you get deeper in a fluid, the pressure increases. And it's because of this pressure differential that you feel this upward force on you. So if the pressure down below is greater than the pressure up above, remember pressure is the density of the fluid times gravity times the depth that you are in the fluid. So the deeper you are, the higher the pressure, the more you're going to feel an upward pressure, which means you feel an upward force. Now, when we submerge an object in a liquid, it displaces the fluid that would fill that region of space. So here I have a bowl of water, and I have a rock. It's actually a piece of granite. And when I put it in the fluid, what happens to the volume, to the liquid level? Well, we can see that that liquid level increased, and it increased by the amount that the rock displaced. This is called the displaced fluid. Now, this led to Archimedes' principle. Archimedes' principle says that an object that is completely or partially submerged in a fluid feels this upward force that is equal to the weight of the fluid displaced. So if an object displaces 2 pounds of fluid, then it feels an upward force called the buoyant force equal to 2 pounds. Now the key here is that this buoyant force is all about the fluid. It's about the fluid that's displaced. It doesn't matter that that was a block of granite or it could be a block of wood. The block material doesn't matter, just the amount of fluid that gets displaced by the object that's getting submerged. If we look at how to calculate the buoyant force, remember that the buoyant force is due to that pressure differential, which results in an imbalance of forces on the object, right? The force down here is going to be greater than the force up here. So if that buoyant force, therefore, is the difference between these two. Now, if we substitute in our pressure equation, right, pressure is force divided by area, so force is pressure times area, right? I get the difference in the force down the bottom, pressure times area at the bottom, minus the pressure times the area above. Of course, we can go in and simplify this a little, take the area out. The area is the same for both of these for this uniform object. And I can substitute in my density or my pressure equation. Remember, pressure was the density of the fluid times the gravity times the depth that were in the fluid or the height. We can simplify this a little more, right, because H2 minus H1 really is just the difference in height here. And when I do that, right, now I have an area times the difference in height, or the height of this object, right, which is a volume. So that leads us to the actual buoyant force equation. The buoyant force is equal to the density of the fluid, not the object, times the volume of the fluid displaced times the acceleration due to gravity. Now notice that density times volume is mass, right? So the density of the fluid and the volume of fluid is just the mass of the fluid displaced. So we could also rewrite the buoyant force as the weight of the fluid, mg. One important note is that when an object is completely submerged, just like with my block of granite here, then the volume of the fluid that is displaced is equal to the volume of the object. So that's when we would use the volume of the object in our calculation. But remember, it's all about the fluid. Now, let's talk about why objects float or sink. I took this right out of your textbook. And while I know you all read your textbook, I thought it would be good to go over it a little bit. In our first scenario, we have an object that sinks. All right, an object that sinks means that the weight of the object is going to be greater than the buoyant force up. So we notice that we have this imbalance of forces here, which causes the object to sink. Now, of course, that means it's accelerating as it goes down in the fluid. And so eventually, when does it come to rest? Well, it comes to rest when it's sitting on the bottom of this beaker, because now I have a normal force. If we go to our second scenario here, we have an object that obviously has less weight than the weight of the fluid displaced, because we see that that upward buoyant force is actually higher than the weight of the object. A good example of this is a beach ball.
The beach ball is very light, so in order to totally submerge it, my assistant Kelly here needs to apply a lot of downward force. If that force is removed, the larger buoyant force causes the ball to accelerate up out of the water. When it is at rest of the water and the forces are balanced, you can see that very little of the beach ball is actually under the water. This is because the buoyant force, which is the weight of the water displaced, has to be equal to the teeny tiny weight of the beach ball.
In our last case here, we have what's called neutral buoyancy, which means that the buoyant force up and the weight of the object is equal. Here it is completely submerged, but this could also be true for an object that's floating on the surface. That's at rest, right? When an object's at rest, the force up has to equal the force down. So an object that is completely submerged but not sinking, that means that the weight of that object is exactly equal to the weight of the fluid displaced. So let's take a look at one type of problem involving buoyant forces. Here I have a block that is tied to a string and submerged underwater. I want you to find the buoyant force on the object and the tension in the rope. I've given you three things. One, the mass of the block, the density of water, and the density of the brass. Notice that density is very close to the density I found for my unknown object in the last video. So first thing I want you to do is draw yourself a free body diagram. Identify all the forces on the block, and then see if you can figure out the buoyant force. Pause the video and see how far you get. Alright, so let's take a look. From your free body diagram, you should have three forces. We have the tension force up from the string, we have the buoyant force up from that pressure difference in the water, and we have the weight of the block down. So our force equation should be that the sum of the forces up equal the sum of the forces down, right? Some of the forces have to be zero because this object's at rest. So we have the buoyant force plus the tension force has to equal the weight. Now, we need to find the buoyant force first before we can find the tension. We know that the equation for the buoyant force is the density of the water that's being displaced times the volume of the water being displaced times the acceleration due to gravity. Remember, it's all about the weight of the fluid displaced. Now, I know the density of the water, right? That's given. But how do I find the volume of the water displaced by this block? Well, it's completely submerged, right? Which means that the volume of the water that was displaced is equal to the volume of the object itself. But how do I find that? I didn't give you that information. Well, I did give you the density of the brass, and I gave you the mass, right? And density is mass over volume. All right, so we can just rearrange that equation, and we can find out that the volume of the block itself is the mass divided by its density. And remember that the volume of the block, because it's completely submerged, is equal to the volume of the water that's been displaced. So if you do that calculation, this is what you get. And now we can just plug and chug. Density of the water, 1,000, times the volume of the water, which is 2.3 times 10 to the negative fourth meters cubed, times the acceleration due to gravity, 9.8. And you should have gotten 2.25 newtons. Remember, the unit of force is newtons. All right, now that we got the buoyant force, it's time to find the tension in the rope. So if we go back to our force equation, right, all we got to do is solve for tension, right? So move buoyant force over to the other side, and now it's just a matter of plugging and chugging, right? We know the mass of the block, it's 2 kilograms. The acceleration due to gravity is in a constant, it's 9.8, and we know our buoyant force. So when you put all your numbers in, hopefully you got 17.3 newtons. If this object wasn't submerged in water, what would the tension force be? Well, it would be the weight of the block, right? 2 times 9.8. So our new tension force is less, right? Because we have this buoyant force pushing up, and this has a name. It's actually called the apparent weight. It's apparently how much it weighs when it's in water, right? You apparently weigh less when you're in water in a swimming pool. And so we call that apparent weight. When I see you in class, we're going to talk some more about buoyant forces. We're going to talk about objects floating and sinking. We're going to talk about ships and hot air balloons. So I'll see you in class.